Hi. And this is a collaborative work with Jiří Vokřínek and Kleiner. So we are interested in having robots to transport stuff around. We are looking at the industrial intralogistics. So for example, warehouses or factories where you want to move things from one workplace to another, or even to automated deliveries by UAVs, right? So one of the important things that you need to consider if you build such systems is how to avoid collisions between the individual vehicles. To ground things a little bit, to have a concrete scenario in mind, let's have a look at this automated warehouse system of a web shop, for example. So you can imagine that then a customer orders a product, and then we look into the database in which shelf is the product stored, and then we want to send a robot from some charging station to pick the product from a shelf, and then move it to some human operator who will take the product and ship it to the customer. So that's the scenario we will want to solve. Formally, we define the problem as follows. So we have a known static map of an environment, and we have a set of locations that we call endpoints that can serve as a destination positions, start and destination positions for the robots. This environment is occupied by a number of robots, typically quite a large number. And we can, and in this environment, we can pick one of the robots and tell him, okay, you go to one of the endpoints. So we can send him at any time to one of the endpoints. What we need to make sure, what is the objective of this problem, is when we order the robots to go to one of the endpoints, we need to make sure that the robot will find a trajectory to the destination that will not collide with any of the robots that are already in the system doing their own stuff. Okay, so if you want to implement such a system, the existing approaches basically are based on two techniques. Quite popular one is the reactive approach, where you just plan your path, ignoring all the other robots. You start following the path, and you monitor your environment for anything that you collide that you can collide with. When you detect a potential collision with some other robot, you compute some local change to your current immediate heading or velocity to avoid the collision. So there's a number of techniques that can do that quite efficiently using linear programming. One of the very popular ones is Orca by Van den Berg, which can do it for a number of robots very efficiently. An obvious disadvantage of this approach is that these collisions are solved only locally. And therefore, it is always possible that we construct a situation that these reactive techniques will not solve. Usually, the robots will just get stuck. They end up in a deadlock. An alternative is to use a planning approach. Basically, what it means in this scenario is whenever one of the robots is assigned a relocation task, we have to stop the system, take the starting positions of all the robots, and plan a coordinated trajectories from the starting positions to their destinations. When we are done, we let the robots follow the planned trajectories. And if they do it precisely enough, we know that we will have a deadlock-free and collision-free motions, right? Because that's what the planner will output. Okay, one of the problems with this approach is that finding such coordinated trajectories is actually NP hard for the case of circles, coordinated arbitrary circles with polygonal obstacles. This is a result that has been long known. It's almost 30 years old. And as you could expect, all the known algorithms have a worst case complexity that is exponential in the number of robots. So that's the problem with planning, that it can be actually intractable to compute those coordinated trajectories. The main contribution of this work is that we characterize a class of environments in which we can compute these coordinated trajectories in polynomial time. So later on, I will explain what are these environments and how do we compute these trajectories. So the algorithm that we use, we call it COBRA. which is a short for continuous best response approach. It's a decentralized approach in the sense that there doesn't need to be any central solver. The robots can arrive to a solution just by communication and by using their own onboard planners. They can plan their trajectories locally. We use to coordinate the computation. We use a token-based synchronization. That means that we have a shared memory with synchronized access. Here it's just a message that the robots pass from one to another. And in this token, we store the current trajectory of each robot. So basically, the token holds an information about what is each of the robots planning to do in future, what trajectory is it intending to follow. So the main idea of this approach is that whenever a robot is assigned relocation task, whenever it's ordered to go somewhere, it tries to obtain the token, and it plans. It uses a space-time planner to plan a trajectory that avoids all the robots that are following the trajectories stored in this token. So basically, it avoids all the robots that are executing the task that were assigned before this relocation task. Before his relocation task, right? So this is a pseudocode of the algorithm, very simple. Basically, whenever I'm assigned a new relocation task, I request this token, so I'm sure that I'm the only one who is planning in the system. Then I find an optimal trajectory that avoids all the trajectories that are stored in the token. For this, I need a trajectory planner that is able to plan with moving obstacles. That is, I need to plan in space-time. Then I take the trajectory I found, I put it into the token, release the token so that the others can plan, and I start following what the trajectory that I just found. And this is executed by each of the robots. So the important property of this approach is that under some assumptions, namely that the environment is static, the robots are able to perfectly, sufficiently precisely follow the trajectories, and that we don't interrupt the robots midway. We're able to guarantee that this will always succeed. So this will always find a collision-free trajectory in a class of environments called valid infrastructures. Right. Okay. So what is a valid infrastructure? Okay. Well-formed infrastructure is so at the beginning, during the problem definition, we have seen that we have a map of environment and a set of endpoints. So the endpoints is a set of points that can act as a start and destinations for each robot. And in the real world, you can imagine them as, for example, parking places or some stations next to workstations, or if you model a railroad network, they can be the stations where the train stops. So these places where the robot may need to stop. So that's an infrastructure. An infrastructure is well formed or has this good property if we are able to find a path between any two endpoints which doesn't intersect any other endpoint. I think it will be clear if I use an example. So for example, on the picture on the left, from your viewpoint, we have an example of a well-formed infrastructure. Here, we can find a path between all two pairs of endpoints that doesn't intersect any other endpoint. In contrast, this is not a well-formed infrastructure because there is no path from this endpoint to that endpoint that would not cross this endpoint with enough clearance. So we guarantee that the algorithm works for this class of environments. A good news here is that the environments that you usually encounter and the environments that we usually build as humans are usually designed this way. So for example, if we look at a road infrastructure as an example, the endpoints would be the parking places, and the map of the environment would be the roads. And from your everyday experience, you can tell that if you start at one parking place and you go to any other parking place, there's always a path that you can follow without crossing other parking places on the road. The same goes for offices or for industrial places. If I want to go from my desk to a coffee machine, for example, usually I don't need to cross places that are usually occupied by people, like other desks or copy machine, for example. Another thing that we can show for this approach is that the trajectory planning that we do at each during each relocation task handling is done in the quadratic time in the worst case. So we have a bound on the length of trajectory planning. So this is in contrast to the general trajectory coordination, which was exponential. Okay, we have done a few experiments in multi-robot simulations. We used two environments. This is an office-like environment. I think this is the University of Bremen, actually. We put up to 30 robots into this environment, and for each robot, we generated we assigned it a random destination as a relocation task. When the robot reached the destination, we have generated another destination and sent him somewhere else. So by doing this, we ensure that the robots are always in motion, going somewhere. We have compared our approach. That is that we plan after each relocation task. We plan a trajectory for the robot using our approach versus the reactive approach. That is that we just plan the shortest path to the destination, and whenever we detect a conflict, we use this ORCA, which is the state-of-the-art reactive approach, to resolve the conflict. So we can see that we have much better coverage. So, for example, in these really dense situations, the reactive approach actually fails or ends up in a deadlock in more than 50% of the cases. So in this particular environment, it's quite unreliable, and moreover, we are getting shorter trajectories. So this graph shows the prolongation due to collision avoidance. So the red line is the prolongation that was introduced by our algorithm, and the blue line is the prolongation that was introduced by reactive collision avoidance. You can also note that the variance of the prolongation is much smaller. Here is an illustration. How does the system work? How does it work in action? How does it look in action? So here you see the robots. The red circles is the current destination for one of the robots. You see when the robot reaches its destination, we just generate another destination for the robot just to keep him moving. Okay, so that was an illustration in the office environment. We've done the same thing for this warehouse-like environment. You see that the results are qualitatively very similar. This environment has less narrow corridors, so it's more easy for the reactive collision avoidance. But still, we have instances where reactive collision avoidance fails. Since we are guaranteed, we solve everything. Again, another video showing how does it look in a warehouse environment, just to give you a feeling of what it does. Yeah, and this can go like this forever. So I just choose the few seconds of the video as a short illustration. Okay, to conclude. The existing methods for multi-robot collision avoidance, there are two ways how you can achieve it. So one is reactive collision avoidance. Well, it's which is efficient, but it's prone to deadlock. You never know whether your robots will actually reach the destination. The second approach that can be used is multi-robot trajectory planning, which is in general intractable. So in this work, we have characterized a subclass of instances or subclass of environments that are actually solvable in polynomial time, and devised algorithm that can be implemented in a decentralized way that can be used for trajectory coordination in such environments. If you are interested in these things, the implementation of the algorithm plus the benchmark instances are available on my website, and I would be happy to help you with running it if you are interested. Okay, so that's it, and I'm happy to answer any questions.